Shadi, let's just get right into it. Let's start with you. A bunch of new features inside image processing and signal processing.
Yes, thanks, Zach. So I'm going to talk about image and signal processing features in version 9. Image processing was new in version 7, but a lot was added over the past 2 versions as well. 9 is going to have a lot new features. And at the end, I'm going to talk about the signal processing features that were new as well in version 9. Let's get started with image processing. A lot of new things got added in version 9, including some interactivity that makes the whole image processing solutions a lot easier to get done. 3D images are new in version 9 as far as rendering, processing, and creation of data out of core processing of 2D and 3D images, and a lot of enhancements in different areas of image processing, including filtering, feature detection, color management, and so forth. Let's get started by getting an image into our Mathematica session. I'm going to take this image out of the slideshow mode so that I can show all of the interactivities. As you can see, once the image is selected, I have a toolbar attached to it in version 9. The first tab allows me to do a lot of different types of selections, including rectangular, circular, or freeform. And once I do the selection, I can, for example, copy them as a list of images and paste them into the session. The other tab that we have, and is very commonly used, is the crop tool. I can crop the region of interest from the image that was just imported, hit crop, and I get the crop version. There are a lot of transformations introduced in this image assistant toolbar, including flipping from right to left or top to bottom, resizing based on the percentage or the actual pixel size, while also keeping, for example, the aspect ratio to resize. Getting access to a lot of information about the image, including dimensions, color space, and so forth. And we also have the option of changing some of the properties of the images, including color space, interleaving, and some others. We also have access to a bunch of image processing filters and functions under the More section. For example, I can go under Image Effects and use the embossing effect, get a preview of what I'm getting after applying that filter, and once I apply, the image is being embedded, the filtered image will get replaced. Note that this is all happening on the image, and that image could be inside of a bunch of code, and that gives us a lot of capabilities for pre-processing the image in order to get the better result out. Let's get the image back again. If I scroll down, you can see that underneath the image, there are a bunch of predictions proposed as the next step. For example, I can go ahead and click the flip button down there, detect some edges using either of the methods that are available and changing the parameters to the edge detection function, hit apply. As the next step, maybe invert the colors, do some blurring using a bigger radius, and maybe do auto adjustment. Once I'm happy with the result that I've got, I can roll up all the processes and get the final result. You can see that all of these interactions are giving me ways of processing the image ahead of time before getting to the actual process for solving a problem, or perhaps just have fun to explore what are the other capabilities, for example, getting to the histogram of this image and then changing the axes, frames, image size, background, and so forth. So a lot of fun interactive versions of image processing are added. Let's get to the 3D images. Of course, one of the biggest features that were added in version 9. Here I'm importing a CT of an engine that was created. This is included in the example data set. And as you can see, the CT image has created a 3D volume that can be rotated, flipped, zoomed in and out, and be explored. I also can create a 3D image from a numeric data set. Here I'm creating a 3D Gaussian matrix, a 41 cube data set, and I can create a 3D image out of that. For example, this can be used for exploring some data creation or manipulation. Here I have the game of life in 2D. I can change the seed to get to a different initial state And then I can see different generation, multiple generations of the game of life happening and visualize it as the 3D volume. I can also create an RGB volume from a set of RGB images and look at it and render it. There are a lot of rendering options available for 3D images. Color function is the option that allows for changing the color function, also known as the transfer function. Here I'm using a rainbow opacity, which is basically assigning a rainbow color to all the pixels and assigning a linear opacity to the values of the volume. So basically all the pixels that are black and represent the background are fully transparent, and all the other pixels have linear opacity based on their values. I can also specify a custom color function. Here I'm using a blend between 4 colors based on the, again, intensity values of the pixels, and I get a different rendering. We also have provided a palette for changing the color function, which is accessible through the right-click menu on the image 3D. Once you're there, you can either choose some of the predefined opacity and color functions from the menu, or you can manipulate by moving the nodes of the color function, or even assigning colors to the nodes by double-clicking on that. Background is another rendering option that is very commonly used, especially with some special color functions like the X-ray, where most of the values are bright and a white background does not show much of the volume. Box option is also very useful, since most of the acquired data set do not have the exact same resolution in all 3 dimensions. Typically in Z dimension, you get a different resolution, and it's typically not as dense. For example, in this case, you can see that the head does not show up in correct proportions of the actual head. And I can set the box ratio so that the volume is rendered in the actual size of the object. It's very common to explore the image 3D or the volumes in order to see inside of a volume. There are 2 common ways in Mathematica 9 to explore a volume. One being clip range, specifying the clip range option that clips away part of the volume. Here, for example, I say all of the x and y's in the xy plane have to be clipped, and I can change the z clip range so that I can basically see all the volume in one dimension. The other common way to explore inside of a volume is to see projections of it in different dimensions. Here I'm changing, again, the slices that are visible in 3 different dimensions and highlighting where I am in each dimension. Similar to 2D images, you can access different properties of image 3D volumes, using image type, image dimensions, compute the histogram, or even do some measurements like compute the mean intensity values or the standard deviation of values. Most of the filters and functions also support image 3D. You can do the same gradient filter that was available for 2D images using a radius 2. So here we are computing the gradient based on a 5 by 5 by 5 local neighborhood. You can also pass the same processing functions to manipulate and do, for example, erosion of the engine that we had earlier. A lot of these images can be found in different fields, like basically medical sciences and biology, material sciences, geophysics and environmental sciences, and so forth. Let's move on to the next topic, out-of-core image processing. With introduction of image 3D and with existence of a lot of large images, it's very important to be able to do out-of-core processing of images. Basically, in this scenario, chunks of the image are imported into the memory, processed, put back to the disk so that very large images can be processed. Here I'm getting a not very large image for the sake of the presentation, but I'm showing that how all of these functions are working with this file that exists in this path in my machine. We have introduced 3 basic functions to do out-of-core processing. First of them is the image file scan. This function basically works by side effects. I have a total variable, and I want to compute the total intensities of this image by accumulating all of the intensity values. I can do image file apply, which is basically the same as image apply for in-core. And it's giving me a file, a path to the file that was written after all the computation was done. So let's import this and see that the inversion, basically 1 minus hash, was done on this image. We can also do local filtering out of core via our image file filter. And again, if I import the created file, you can see that the maximum filtering has been done out of core. There are also a lot of new features added to different areas of image processing. Enhanced color management is one of them. If I import this coneflower and get the options color space, you can see that an object color profile data is sitting there. So basically, this is the ICC profile that has come with the JPEG file. And this profile can be used for converting the color space of the imported image to any other color space, including the 3 new CIE color spaces that we have added in version 9. Feature detection is another nice feature that we have added. Here I'm doing a face detection, finding all the faces bigger than 100 pixels. And I'm highlighting the rectangles showing the faces in the image. We also have feature tracking added into version 9. Here I have a list of images. I track all the features in the images that were specified. And I highlight the found points in each frame so that you can see the track points, and then do a list animate to show the tracking. Here you can see the result. It's definitely important to mention that this highlight image, along with a lot of other utility functions, were added into version 9 that I'm not going to show in this talk, but I definitely encourage you to look at them in our guide pages. Here I'm also going to show a segmentation based on local texture using the new in9 Gabor filter. I'm creating a Gabor magnitude filter based on the Gabor filter. Here I'm doing Gabor filtering along two directions, 45 and minus 45 degrees. And you can see that the texture is highlighted, either the stripes that are along 45 degrees or minus 45 degrees are highlighted in the filter. And if I compose a binary version of the two filtered images, you can see that the image was segmented based on the local texture. Let's move on to signal processing. There are a lot of visualization and analysis of signals added. We have added capabilities for filtering and processing of signals, including audio, images, and other data. There is also capabilities for designing digital and analog filters. Let's import a sound file here in Mathematica and compute the spectrogram of it. We can also compute the periodogram using different window lengths. Periodograms can be also computed and visualized for images. Here I have a half-toned image of a face. And in the periodogram, you can see high frequencies as well as low frequencies features of the image. Image periodogram can also be applied to 3D images, like this MR image of the knee. And in order to see the inside of this 3D periodogram, let's use a clip range that clips out parts of this volume. As far as filtering goes, we have added, again, a complete set of new filters that work with frequencies. Low-pass filter is one of them. Here I'm specifying the cutoff frequency for filtering that noisy signal that I just created. And you see as I increase the cutoff frequency, the signal is smoothed. I can also run the same low-pass filter on the half-toned image from the previous slide. And if I assemble the before and after, you can see that all the low-frequency features are preserved and all the high-frequency ones were removed. We have a full support of designing filters in version 9, FIR, IIR, and analog filters. Let's get started with FIR filter design. There are 3 classical methods for directly creating FIR filters, including least squares frequency sampling and equiripple method. Let's take the least squares method that tries to design the filter by minimizing the mean squared error between the ideal spec, being low-pass filtering, all the frequencies below 0.8, and filtering everything else. Here is the magnitude response of the filter that was just created with the least squares filter kernel, the blue plot, and the ideal filter specification, the red plot. The area that was shown in this graph is what is being minimized with the least squares filter kernel. This filter can be applied to, again, signals. Here I'm getting one row of this image, and then filtering it using the H filter that I created using list convolve, or it can be passed to image convolve as a 2D kernel and used for filtering an image. Least squares method is also known as the window-based method. Here I'm using a hand window. I'm creating a hand window, and I'm multiplying it by the created filter to apply a smoothing effect to the filter. If I look at the magnitude response of the ideal filter specification, the originally designed filter, and the smoothed version, you can see that this red plot, which is the smoothed one, is even diminishing the mean squared error more. You can choose from different window sets. We already basically support about 25 windows in Mathematica 9 based on the desired attenuation of the filters. Here I'm showing you 4 of the windows that are supported in version 9. Digital filters can also be designed by transforming an analog prototype to its digital equivalent using the bilinear transformation. Here I'm creating a Butterworth filter, an analog filter, and I'm using 2 discrete time model to convert that to a digital filter. Let's take a look at the impulse response of this IIR filter and use it again to filter the row of the image that we extracted in the previous slide, or use it for filtering the whole image. As mentioned in the previous slide, we have analog filters. Butterworth, Chebyshev type 1 and 2, elliptic, and Bessel filters are the ones that are supported in Mathematica 9. Here I can create different filters of different orders, and I'm showing you the transfer function of those. One can take a look at the Bode plot of either of these analog filters that were created, extract the poles of the Butterworth filter or any other one, even visualize the poles, or look at the response of the analog filter to different inputs, including, like in this, manipulate triangular or square wave with different periods. This was basically my talk for image and signal processing in version 9. Hope this actually gives you a good introduction to the new features in version 9. And feel free to explore all of our documentation and new features in Mathematica 9.
Shadi, a couple of follow-up questions for you. First off, do we support stereo sound in our functions?
Yes, actually, let me show you an example sound data set that we have. Let's take a look at the full set. There are a lot of sound examples in the sound example data set. There are a couple of stereo sounds. I think the rolling coin, if I extract the channels, or actually channels, you can see that this has 2 channels. And then I can compute, if I import the sampled sound list, typo, and then compute, for example, the spectrogram of the imported sampled sound list. It's accumulating the sound of 2 channels and giving us the spectrogram. I can also do the periodogram of the imported sound, and you can see in this case 2 plots are provided, are computed for the 2 channels that were imported. I should perhaps use a window size in that case, let's say 1,000 samples, and see a smoothed version.
Very nice. One more question before we move on.
Yep.
Do all image processing functions support image 3D?
Documentation for individual functions, of course, say whether or not they support image 3D. Not all of them support image 3D. First reason, so many of the image processing functions are not even well defined for 3D. Just because version 9 had to come out eventually anyways, we didn't have time to add support to all of our functions, but the ones that do make sense for 3D are definitely going to be supported in future versions.
All right. Well, if you need to find some sample code or some examples about image processing or signal processing, head over to the Documentation Center. You can also learn more at wolfram.com/mathematica.